Today we have an interesting question from the Korean SAT. It is the 30th question from the 2018 September mock SCAR type paper, which is taken by STEM students. Only 4% of students got this question right, and so it's ranked the hardest in the whole test. Pause the video and try solving it for yourself. Now what we can see is that we have two functions, f of x and g of x. F of x is a defined function here, and g of x is a quadratic, any quadratic. And at the end we see that we want to find the value of g prime of k minus half, which means we're interested in the quadratic g of x. So we'll keep that in mind while solving this question. We'll start by attempting to draw or at least have an idea of each of the functions f of x, g of x, and h of x. So we'll start with what's clearly defined, which is f of x. So what we can first do is trying to differentiate it. F of x equals ln e to the x plus 1 plus 2e to the x. And if we differentiate that, from the chain rule, we'll differentiate ex plus 1 at the top, so we just get e to the x. And at the bottom, we will get e to the x plus 1. And at the end, that will just be 2e to the x. So we can see that f of x is always increasing, as we know that this is always greater than 0. And we can obviously see that by testing its limits. So if x goes towards infinity, e to the x will be infinity, e to the x plus 1 will be infinity, 2e to the x will be infinity. And when x approaches negative infinity, we get e to the x approaches 0, e to the x approaches 0 plus 1, so 1, and 2e to the x approaches 0, which means the overall function approaches 0. So since f of x is always increasing, there are no critical points. Since the quadratic isn't defined in the question, so g of x, we'll simply define this as ax squared plus bx plus c. So let's draw these two functions roughly on a graph. We don't know everything, so we'll just do our best and make a guess. So f of x is always increasing, approaches infinity as it goes to infinity, approaches 0 as it goes to negative infinity. So it'll probably look something like that. And g of x, we'll just guess. We don't really know anything, so we'll just draw something like that. So we have g of x here and f of x here. Moving on to this absolute value h of x. So h of x is equal to the absolute value of g of x minus f of x minus k. Before we try working with this function, let's think about what h of x actually represents. We see here that inside the absolute value function, we can see that it's simply the difference between g of x and f of x minus k. But since it's an absolute value, it's not just any difference, but we can interpret it to be the distance. So that means if we use our rough sketch here, we'll draw another graph below that corresponds to h of x. So h of x is finding the difference between g of x and f of x minus k. Well, f of x minus k is just f of x here, but transformed k units to the right. So it doesn't really have a huge impact on our graph. So if we just use our rough sketch here, h of x would start with a big distance, become 0 when they intersect, become bigger again, and then 0 when they intersect again, and then increase once again. So it will have this kind of shape. Let's look at the first part of this question. It says here that the function h of x has the minimum value g of k when x is equal to k. So what that means is that the minimum value we can find at the coordinates k, g of k. So in the context of our interpretation of h of x as telling us the distance between f of x and g of x, what does the minimum tell us? So as we've already discussed, and from looking at this graph, we see that when x is equal to k, the distance between f of x and g of x is at a minimum. So in this example, when two functions intersect, the minimum would be 0. So we can see that quite clearly. We can see that when the two functions g of x and f of x intersect, the minimum of h of x is 0. So keeping that in mind, let's start by substituting x equals k into h of x and let that equal g of k. So we will get h of k equals the absolute value of g of k minus f of k minus k and absolute value, and that equals g of k. And so that would just be g of k minus f of 0 is equal to g of k. What we want to try to do now is to get rid of this absolute value. Starting with the definition of the modulus function in its general form, the absolute value of x is x when x is greater than 0 and negative x when x is smaller than 0. We can set up two possibilities for h of k. If we consider the inside of the modulus function as x, so when the inside of this function is positive overall, we would have g of k minus f of 0 equals g of k. And when we have it so that the inside of this function is negative, we would have negative g of k plus f of 0 equals g of k. Now let's solve for each of these possibilities and let's see which one is feasible. So in our first case here, we can just use algebra to move this to this side, and we get this strange equation f of 0 is equal to 0. So if we substitute 0 into our function f of x, we see that it simply equals ln of e to the x's, e to the 0 is 1, 1 plus 1, plus 2 e to the x's, 2, e to the 0 is 1, so 2 is equal to ln 2 plus 2. Now we know for a fact that is not 0, which means we must rule out this case as not being possible. We'll move on to the other possibility. So here we can see that f of 0 is equal to 2g of k, which means that since we're interested in g of k at the end, we will find that g of k is equal to half f of 0. Now we already found what f of 0 was here. We can rewrite this as half ln 2 plus 1 or ln root 2 plus 1. And this becomes our only feasible version of the absolute value function, and this will also become our first equation, which we will use later. And one additional thing is that since we have only found that one case of the absolute value function is feasible, we can rewrite h of k as f of 0 minus g of k. So we are only considering this case as we have found the other case is not possible. And we can also write h of x as f of x minus k minus g of k. Going back to our sketch, we can now make some revisions. As we know that the minimum value of h of k is ln root 2 plus 1, and we know that ln root 2 plus 1 is positive, we know that there must be no intersection between f of x and g of x. So we can make some changes to this function. So can gx be here, for example? As from our graph, it might seem that these two graphs, g of x and f of x, will never intersect. However, we know that exponentials always increase faster than quadratics, so which means at some point that's off this graph, they will intersect. So what that means is g of x must be placed here. So in this example, we would have something like, we'll have it big, then we'll have a minimum somewhere here, and then big again. So this might represent roughly our sketch of h of x, and this is g of x. For h of x, which we have now defined, revised and defined as this, f of x minus k minus g of k, we have two differentiable functions, which means we can differentiate h of x. So since we're dealing with the minimum value, which is at x equals k, we know that h prime of k is 0. So we'll write h prime of k as that being equal to f prime of 0 minus g prime of k. And that is equal to 0. So we can start by finding f prime of 0. F prime of 0 is equal to e to the 0 over e to the 0 plus 1 plus 2 e to the 0, which is equal to 1 over 2 plus 2, which is equal to 5 over 2. And now we can find that minus g prime of k is equal to negative 5 over 2, and thus g prime of k is equal to 5 over 2. And so we'll list that as our second equation. What we actually want to do just now is, instead of writing it just as g of k, we might also want to write it in terms of our general quadratic equation, ax squared plus bx plus c, as maybe in the end we might want to use that to solve for each of these variables simultaneously. So we can write here, it's quite simply, g of k is just ak squared plus bk plus c, and that's ln root 2 plus 1. And if we differentiate ak squared plus bk plus c, we just get 2ak plus b is equal to 5 over 2. And so this is also our first equation and our second equation. Now we move on to this next part, which deals with a maximum value in the closed interval k minus 1 to k plus 1. And the reason why this might seem a bit tricky is because we're not actually dealing with the real maximum of the function, but the maximum in this specific interval k minus 1 to k plus 1. And actually, if we look at our rough sketch of h of x, we know that there can't be a local maximum that we can actually find the value of. So it does make sense that they're giving us the maximum value in a closed interval. So we know that the minimum value is at k. So maybe that's somewhere here, which is where the distance between the two functions are the smallest. And then we also could label k plus 1 as somewhere here, k minus 1 as somewhere here. And so this is our closed interval. And now we want to see that the maximum distance between the two functions must be either at k minus 1 or k plus 1. So that's pretty intuitive to see. Looking at this graph, we know that it must be at either of these values. But now it's a game of finding which one is bigger. So we can write h of k plus 1 just by plugging in k plus 1 into our function h of x, which we have here as f of x minus k minus g of x. So we will write this as f of k plus 1 minus k minus g of k plus 1. And for k minus 1, we have f of k minus 1 minus k minus g k minus 1. So moving back here, we can write this as f of 1 minus g of k plus 1. So let's keep continuing with this equation. Since f of x is defined, we can just plug in 1 into our f of x here. So here we will get ln e to the 1 plus 1 plus 2 e to the 1 minus g of k plus 1. And down here we have f of negative 1 minus g of k minus 1. So again, we'll just plug in negative 1 into f of x and get ln e to the negative 1 is 1 over e plus 1 plus 2 e to the negative 1 again, so 2 over e. And let's just write this ln as a nicer simplified form by multiplying everything by e over e. And so we will just get e plus 1 over e plus 2 over e. And of course, we can't forget the g of k minus 1 at the end. So now what we could do is, since we have two equations here, 1 and 2, we want to find the difference between the two equations. And since we've interpreted h of k as a distance, and we're looking for the maximum, we want to see which equation is larger. If we do equation 2 minus equation 1, and we get a positive number, then equation 2 is bigger. And if we do that and we get a negative number, then equation 1 is bigger. So we'll just do this subtraction, and we see if our answer is positive or negative. So we will be subtracting this equation from this equation. First of all, we'll get ln e plus 1 minus ln e plus 1 on e. So first of all, we'll get ln e plus 1 on e minus ln e plus 1 plus 2 on e minus 2e minus gk minus 1 minus minus, so plus gk plus 1. Let's start by simplifying the first half. So using the law of logs, we get this is simply ln e plus 1 over e plus 1 plus 2e take 2e minus g of k minus 1 plus g of k plus 1. And that just cancels to get 1 over e. Using the fact that ln is just log base e, we get negative 1 plus 2e. And let's write this second bit as the general quadratic, since g of x is the general quadratic. So we can write this simply as, we'll put the plus at the top. So we have g of k plus 1 at the top. We have a k plus 1 squared plus b k plus 1 plus c. At the bottom we have minus a k minus 1 squared plus b k minus 1 plus c. So we are minusing, so first of all c cancels. So expanding this, we get ak squared plus 2ak plus a plus bk plus b, and c is gone, minus ak squared minus 2ak plus a plus bk minus b, and there's no c. So then we get this cancels, this cancels, and now we're left with 4ak plus 2b. And if we go back to our equations, we see that 2ak plus b equals 5 on 2. So we'll just write here 2ak plus b equals 5 on 2. And we can actually write this as 2 times 2ak plus b, right? And so we'll just substitute that in and we get 5. 2 times 5 on 2 is 5. So that means if we write this whole thing, when we subtracted equation 1 from equation 2, we get negative 1 plus 2 on e minus 2e plus 5. So let's have a look. If we go back to the question, we see that they've given us an approximate value or the range of e. So it falls between 2.5 and 3. So let's just say that e is around 2.7. E is around 2.7. So we have negative 1 plus 2 over 2.7 minus 5.4 plus 5. So first of all, this would equal around 0.66. So you have negative 1 plus 0.66, negative 0.4. So we see that that's definitely less than 0. It's negative. So we'll go back and we know that this is negative. So what does that mean? That means equation 1 is larger than equation 2. That means the maximum lies at k plus 1 with a maximum of h of k plus 1. So max at x equals k plus 1. So that's in our sketch. Max is here, k plus 1. So we can write this as our third equation. Since the question gives us what the maximum value is, we can write this as h of k plus 1 is equal to 2e plus ln 1 plus e on root 2. And remember, we've written h of k plus 1 using f and g. We have ln e plus 1 plus 2e minus g of k plus 1 is equal to 2e plus ln 1 plus e on root 2. So we have g of k plus 1, or negative g of k plus 1, is equal to 2e plus ln 1 plus e on root 2 minus ln e plus 1 minus 2e. So first of all, we can see these two cancel. And using the law of logs, this goes to the bottom, which means this and this cancel, which means g of k plus 1 is equal to ln 1 on root 2. And let's use the law of logs again to get ln root 2 to the negative first power, and that goes to the other side. So we have g of k plus 1 equals ln root 2. So this will become our third equation. And again, we'll write this using our general quadratic equation. We have a of k plus 1 squared plus b of k plus 1 plus c is equal to ln root 2. I guess now we have the tools to probably try to solve the actual final answer. So the final answer here, we see that we want to find the value of g prime of k minus 1 over 2. But the problem here is we know that we have 4 variables. We have a, b, c, and k. Since we have 4 unknowns, we should have 4 equations to solve for each of them. But right now we see that we only have 3 equations. So what should we do? Because from what we can see, we can't make any more equations from the information we've been given. So for now, we'll just start by trying to write this out, g prime of k minus 1 over 2, and see maybe we don't have to solve for each of these variables individually, since the question isn't actually asking the value of a, b, c, or k specifically. So what we can do is write out g prime of k minus 1 on 2. We can write this as 2ax plus b, so 2a k minus a half plus b, which is 2ak minus a plus b. And we already have the value of 2ak plus b, which is a 5 on 2. So 2ak plus b is 5 on 2. So this is 5 on 2 minus a. So the only thing that we need to take us to the answer is to find the value of a. So let's have a look. Since we've already used 2ak plus b in our substitution, maybe we can have a look at equation 1 and equation 3. And you'll also notice that they're quite similar in that they are both the original version of the quadratic equation instead of the differentiated version. We could try another simultaneous equation strategy. Maybe we'll take away equation 3 from equation 1. So we can write that as ak squared plus bk plus c is equal to ln root 2 plus 1. And at the bottom we will write a of k plus 1 squared plus b of k plus 1 plus c is equal to ln root 2. So we're minusing these. So we'll write the second equation, we'll expand it. We'll get ak squared plus 2ak plus a plus bk plus b plus c is equal to ln root 2. Since we're finding the difference between this equation and this equation, we can do a few cancellations. So this cancels, c cancels, bk cancels, ln root 2 cancels, and now we have negative 2ak minus a minus b equals 1. Let's multiply both sides by negative 1. We get 2ak plus a plus b is equal to negative 1. And again, we have 2ak plus b is 5 on 2. So we have 5 on 2 plus a equals negative 1. Therefore, a is equal to negative 7 on 2. So now all we have to do is substitute a equals negative 7 on 2 back into our equation here. 5 on 2 minus a is equal to 5 on 2 plus 7 on 2, which is equal to 12 on 2, which is 6. So our final answer is 6.